Today on Building the Open Metaverse.
Artists have lived with those sorts of budgets for their entire lives, expecting, okay, you give me this number and I have to optimize my content in this particular way. And now that that's no longer true, it's very surprising to them.
Welcome to Building the Open Metaverse, where technology experts discuss how the community is building the open metaverse together. Hosted by Patrick Cozzi from Cesium and Marc Petit from Epic Games.
My name is Marc Petit, I'm from Epic Games, and my co-host is Patrick Cozzi from Cesium. Patrick, how are you?
Hey Mark, I'm doing well, and I'm really looking forward to today's episode. As you know, I really love computer graphics, but within computer graphics, my favorite topic is massive models and everything that goes into doing that efficiently, and I know we're going to learn a ton today.
Because our guest today is a colleague of mine, Brian Karis, who is an engineering fellow at Epic Games. He has worked on the development of various graphics technology for Epic, including Nanite, and he's also known for his work on real-time rendering and physically based shading techniques, which have helped to advance the state-of-the-art in computer graphics. Brian, we're happy to have you with us. Welcome.
Hello. Nice to be here.
So Brian, we love to kick off the podcast where we ask our guests about their journey to the metaverse. So could you tell us about your background?
Have been interested in computer graphics for a long time. I wanted to get into that, and specifically real-time graphics coming out of school. So the best place to do that is in video games. So got into the game industry almost 20 years ago now. Worked at a company called Human Head Studios for a number of years. Worked on Game Prey and some following projects. And then came to Epic, and I've been at Epic for a bit over 10 years now, working on Unreal Engine. Specifically on the Nanite front, it's been a long journey of a particular goal, a particular dream that has spanned a good amount of those years. Wanting to give artists more freedom from the sort of budgets that have constrained them over all my experience working in video games. I've just seen throughout that time working on many different games over multiple generations of hardware that no matter what new hardware comes, there's always this worry about how much memory you have and how much compute power you have to be able to render the geometry. And each time it's this just incremental improvement of number of triangles, number of draw calls. That sort of thing. And it seemed like it shouldn't be necessary given some other technologies, other virtualization that existed for other things. So it had been a goal of mine for a number of years to try to tackle that in the specific domain of geometry. And the kind of culmination of that work is Nanite that shipped with UE5.
Can you explain to our audience what is a virtual geometry system and why do people feel like it's magic?
The reason I call it virtual geometry, it's a lot of things. There's a lot of different systems there that end up solving some different problems. But the reason why I kind of wrap it up with as virtual geometry in that sort of moniker is keying off of some tech in the past and its properties, building off of the idea of virtual memory. Which is this concept of being able to have a very large memory space, or bigger than the amount of RAM that you have in your machine, and being able to move bits of memory, page them in and out from the physical memory off to disk, so that you can simulate the concept of there being much more than there's actually a physical space for it. That my personal experience with that being really powerful came from my experience with virtual texturing. So I had written a virtual texturing system back before I joined Epic. I also wrote the virtual texturing, or a component of the virtual texturing system that's in UE5 right now. And I'd seen the sort of impact that had on artists' work in the various projects that I'd been on with that, especially ones that are older, that we had much more constrained hardware at the time. And just seeing the artists being able to make these just massive textures is like 4K textures from on the console generation of the Xbox 360 and PS3 to be able to ship, create and be able to ship 4K textures on just all sorts of things. and that virtual texturing system enabling that, and the sort of freedom that the artists get, the losing of those constraints, just how much that frees them to be able to be more creative and to get at the thing that they are really envisioning. So seeing those sorts of properties and trying to translate them over to geometry, which they had still had those constraints. They were able to make giant textures, but they were still stuck with these specific budgets for various forms in the geometry realm, specifically poly count and draw calls. So trying to bring that sort of experience over, not necessarily the particular technology that enabled it, just translate it over, because it doesn't translate all that well, but trying to translate over that experience from the artist's point of view of not having to worry about those budgets. So what that means in practice is that, again, like the virtual memory sort of analogy, there is this paging of data that is coming off of disk, such that only the set of memory, the set of triangles and stuff that you need for that particular view that you're using at that moment in that frame is what needs to be in memory. But parts that don't really translate from the virtual memory analogy is that you only need to draw that set of triangles that is actually visible, or a close enough set to that, and a good estimation of what is actually needed to render those final pixels. And because of that property, or if you can get it right, or if you can get it approximate enough, it means that the performance for rendering that frame scales not with the scene complexity, but scales with the number of pixels that you have on screen, which basically means it's somewhat of a constant from the artist's point of view. They can add in whatever they want into the world with whatever complexity and richness, and it still costs approximately the same for 1080p or 4K or whatever their resolution that they're rendering at. They can add in one object, 1,000 objects, 1,000,000 objects, or that one mesh can have 1,000 triangles or 1,000,000 triangles, and it all comes out to basically the same cost.
The level of and incredibly liberating to be able to throw all the complexity that you want and still get the performance out of the system. So
to answer that question of why does it seem like magic, I guess it's just because artists have lived with those sorts of budgets for their entire lives, their whole careers. They're just expecting, okay, you give me this number and I have to optimize my content in this particular way. And now that that's no longer true, it's very surprising to them. And it's actually been kind of funny to see some of those habits still linger, even with people that have used it for a little while, because I still get questions of like, oh, well, how do should I be doing this thing or that thing? Or that they see that the frame rate in their particular scene isn't hitting the frame rate that they want to ship at, so that they start attacking the typical ways that they would optimize things. And then it turns out that doesn't really help. Some of the typical ways that you're used to optimizing, or that they're used to optimizing, are just different now. It just has different properties. So I think a bit of that feeling of magic is just feeling of foreign, because it's what they have grown up or what they have been trained to do.
So over the past year, you had a front row seat at seeing the Fortnite team use the technology. Any use of the technology that was unexpected and surprised you?
I guess yes and no. So not no in the sense that I was involved in the planning of it. So there was a lot of just the uses that was planned for and developed for, as well as where we're trying to get the team to use it, where I had been on multiple of these demos so far that had already shipped with using Nanite, and that team hadn't used it yet. So a lot of it was training them in the experiences that we had already had shipping demos. So a good amount of it was telling them the practices that we had already learned, do these things. But there were areas that we pushed on. It's hard to say that I was really like surprised, because some of them were just part of the plans. But I think we definitely shipped the performance that it ended up being was a bit surprising. In particular, what I'm referring to there is the use in foliage. So I've said from the get-go in our very first talk and documentation about Nanite was that it should not, just from a theoretical point of view, work well for foliage. I just knew for a fact that it was not going to work as well, but I was expecting it to just not really work well at all. And a big use case in Fortnite Chapter 4 was in foliage for trees and grass. And that was a thing that just the team had experimented with and they were wanting to push. So it wasn't a surprise that they did it, because I knew that was part of their plans. But it was a surprise that it worked out. So that we've seen further examples of that in the Opal demo. I'm not sure what we called it externally, the Rivian demo that we just showed off at GDC. So it's still an area that you need to be very careful, because it's not as automatic as how I was kind of explaining things for other types of geometry, specifically this sort of aggregate stuff that's like Swiss cheese filled with holes, or a bunch of independent elements that are connected to one another, like blades of grass or leaves in a tree. They don't work as well, but it has surprised me that they work well enough that we're able to ship a 60 hertz game and able to ship a demo with these massive forests. It still needs, that particular demo was kind of crazy in pushing the complexity.
So Brian, maybe even stepping back a bit just on geometry in general, right? You spoke about the inspiration from virtual texturing and now virtual geometry. Do you want to speak a bit about the unique challenges that geometry has compared to textures?
The problem there is purely just a memory one. If you have the hardware is already good at level of detail. Textures have had bitmaps for pretty much as long as we've had hardware acceleration. And mapping a texture is a fairly trivial operation. Just downsampling a texture by an x power of 2 is a trivial thing to do. And the hardware picking which one of those bitmaps to sample from any pixel is a very easy operation for it to do. So that sort of level of detail and the cost of the data being used is not one that really impacts the frame rate at all. Really, it's just a memory management problem. But on the geometry side of things, that's not true. All of those various properties, well, not all of them, but the things that I was just talking about, those properties are just not really true for geometry. It's not trivial to create levels of detail of meshes or whatever form your geometry is in. Even voxels are easier, but still not trivial in exactly how it does its level of detail. But particularly meshes are complex to try to create a level of detail of, far more complex than just downsampling a texture would be. And then to draw that bit of geometry on screen, that has a performance impact. So having a higher resolution texture doesn't drop your frame rate, it just consumes more memory. But having a higher poly mesh, if you just draw it naively, all of the triangles, it scales linearly with the number of triangles. Trying to turn that into something that's a non-linear scaling, either a log n sort of scaling, or having it be constant scaling with the resolution, like I was saying the kind of goal is for virtualization, is one that's just not really a direct translation for meshes. So there needs to be, you need to have this level of detail concept, and that level of detail needs to be not something that happens globally. The entire thing changes. It has to change in relation to what you're seeing on screen. So say, for example, you've got a giant mesh, just massive in the scale of it's a mountain. You don't want to change the level of detail of the entire mountain at once. You want to have the stuff that's close to you be at a higher density than the stuff that's further away from you, to have it so that once it gets projected on screen, they result in approximately the same size triangles. So to have those things go at different levels of detail means you want to do that in a continuous and seamless manner, so that you're not causing any sort of like cracks as one thing switches and another one kind of stays at a lower resolution. So there's a lot of problems that show up in the geometry area that just aren't really problems with textures. Like, at a texture to have two different resolutions right next to one another, it's not like you see through. There's no causing a break. You can have those texels be at two different resolutions right next to one another. It doesn't cause any problems.
So Mark, just stop me if I'm getting too geeky. But so Brian, is it using like a hierarchical level of detail approach, or is it doing like a compute shader based continuous LOD?
It is compute shader based, but yes, there is a hierarchical level of detail as the basic structure. So there is a hierarchy of triangle clusters, and the clusters are just chunks of triangles in the form of, and in Nanite in particular, they're like 128 triangle clusters. And it creates a hierarchy out of those clusters and picks which kind of cut of that hierarchy it wants to draw at any particular frame. And that's also the form of which it streams it from disk into memory in that same sort of granularity. And then when it's doing that, when it's drawing those on screen, it's picking not just the level of detail, but also what is actually visible. So it'll do frustum and occlusion culling to draw just the stuff that is that you can see.
Because I remember when I joined Epic in 2016 and Kim Libery was showing me around and he pointed to your office. I think it was next to his second floor.
Uh-huh.
No windows, if I remember well, and saying, you need to leave these guys alone because if they succeed, this is going to change everything. It was 2016. So how long did you think about that, and what was the process to solve such what looks to me like a huge technical problem, technical innovation?
If I wanted to be very generous, I could trace back some of the sort of thinking and goals that I've had since some of the earliest days that I've tried making computer graphics sort of prototypes. But if I was more realistic, I would still trace it back going over well over a decade of work. And not just to this point. I've been working at Epic for over a decade now, but Nanite's been out for a number of years. So to the point where Nanite was actually like a usable prototype, it was still like a good 12 years or something of thought. It wasn't actually work. I didn't have the opportunity throughout all that time to work on these ideas because there was other responsibilities, other priorities of things to do. So I worked on, while at Epic, I worked on physically based shading. I worked on character shading, skin shaders, eye, hairs, that sort of stuff. I worked on temporal anti-aliasing, which is a pretty important component for UV4. So there was other things that needed to be done, other priorities that happened throughout time, that meant that I wasn't able to always work on this idea. But it was a very consistent idea for me going on for, off the top of my head now, I don't remember where it started, but maybe 15 years ago was where I really got interested in my free time of just like researching and ideating on how it could be done. And those ideas weren't what Nanite actually turned into. Like the approach that Nanite takes is not where I started. It's not like I had this one brilliant idea 15 years ago or something. It was just like, if only I could work on this. No, it was, I want to solve this virtual geometry problem. It was a goal that was consistent over all that time. And I had different ideas throughout that period. And I think that this could work. I would explore what it would mean, read all sorts of various research papers, just kind of think about it in my free time of what I thought would be a good solution, and then realize that there were just like some like really core flaws with that approach, and then think that there would be, okay, there's a different approach that doesn't have those flaws. Think about that for a while, and then find more holes in that and kind of switch and shift. So the version of it, so kind of like the core framework that that matches the Nanite, how Nanite currently works, is one that has lasted longer than some of those other ideas, but was not the one that has existed throughout all that time, or it was a goal that existed throughout it, and not a single idea, approach, or algorithm sort of thing. But yeah, there was a point there back in 2016, probably earlier than that. Actually, I know earlier than that, of an idea that was pretty similar to what Nanite turned into, minus a few kind of important components. So that sort of hierarchy of triangle clusters was, it's hard to date exactly where some of these ideas landed, but yeah, probably in that time frame, that was already a pretty well-formed concept in my head. But there were other things that were not at that time, like the approach that we take for rasterizing those very small triangles highly efficiently. We take the software approach where we have a compute shader that can rasterize these triangles faster than the hardware rasterizers can do it. And that was something that only really came in later in the process, after I explored some alternative approaches that were totally different. Like I spent a bit, even after I had this idea that I was pretty confident in, for reasons of doubt, reasons that there were some advantages of going in a voxel direction that I thought was worth exploring, even though it wasn't something I really believed in at the time. That I just thought it was necessary to explore it such that I could really be confident that this other direction, this triangle mesh-based direction, was actually the best one. But I thought I had to do the due diligence and check out this alternative that I didn't end up going with. But in that process, I discovered an approach for faster triangle rasterization.
So you did take the time to explore an avenue that you did not believe in.
At the time, it felt stupid. I spent a good 6 months exploring voxels, and I came out the end of it what felt like a failure. I went in not thinking it was going to, I wasn't really believing in it. So I was trying to do due diligence just to say, all right, well, there's other alternatives. I want to rule them out. And I thought I was going to do that fast. Like I was trying to take this approach of, let's just prove that it's not that, and I'll go back to doing the thing that I was doing. And I found that it is incredibly difficult to try to prove that an idea can't work. Not that a particular version of it doesn't work, but that it can't work. Because there's always the next follow-up was like, oh, but if I change this thing maybe, or whoa, but what if that? And it's never ending. So each one of them, even if you get is like, well, that's not really working, but if I tweak this thing, maybe it could. When in every single step is like, well, do I believe that it will? Not really, but maybe it does. So yeah, it came to this point of just, I need to cut this off. This doesn't seem to be going in a direction that's working out. So yeah, I felt after that time that I had wasted time. I felt bad about it. I felt bad trying to defend the time that I felt like I'd wasted to my bosses and leads at that point. That it was just, I had just burned 6 months with nothing as a result. And I tried to hold up some of these other discoveries of like, yeah, but I came away with this thing. It wasn't what I was looking for, but I came away with something. And yeah, I felt bad at the time, but in retrospect, you need to go through experiences like that. You need to have that sort of wandering through the desert to find things. And also I think it's important for an inventor, a researcher, an engineer in general, but just anyone who's trying to explore kind of the boundaries of technology, anyone whose job it is to do that. You need to work on frivolous things at times. You need to explore ideas that seem interesting to you, but don't necessarily have a use yet, but one that your own intuition says, this seems interesting. Maybe this is useful for something in the future.
I think it's a very interesting lesson if you are a CEO like Patrick or running technical teams about you can't dictate innovation. I mean, you have to let process unfold, and you have to wander around a number of things. So
Yeah, it's not time wasted, it's just time invested. And I mean, ultimately, Brian, it seems like you leapfrogged research and you did it at a production scale of Fortnite and Unreal Engine, which is pretty cool.
To give credit, though, there was a good amount of time that it wasn't in production. The point at which it actually was able to make those big leaps forward was the time that I was kind of left alone to work on this for a year or two. And that was the point where it really went from, hey, I've got these ideas in my head. I'd really like to work on this, but we've got to ship Paragon. I really got to work on this, but we've got this GDC demo that's got some photorealistic character in it. We need to work on that. We've got, etc. There's, a whole line of those happening at Epic and before at game studio as it worked before Epic. There's always the short-term priority, and when you want to work on something that's like long-term vision, it's very difficult to do long-term tasks just kind of interleaved with other stuff. So yeah, it happened at a fairly production-focused company, but there was finally got the opportunity at Epic due to a window that happened due to other circumstances. It just that was that lucky moment that I got to explore those ideas, and were able to have enough time to build up a prototype to prove the potential value. And then once we had that, then it was very easy to defend that, I should be spending more time on working that because I had something to show. Here's the potential of it, and it's not just an idea that I'm telling you about. It's like, oh, look, I've got something kind of working. We should build that out. But to get from the, idea in conversation to a prototype, that does need some amount of protected time.
So, Brian, I wanted to ask you a bit more on the geometry representation. So this season on the podcast, Marc and I have been learning a lot about NeRFs from some of our guests. Then also Marc and I are involved in the Metaverse Standards Forum, and folks talk a lot about different types of geometry representation, like subdivision surfaces. So I know you said for Nanite you're using triangles right now. As you look towards the future, do you think that you would mix and match any other representations?
Of course, it's hard to predict the future, and it's hard to commit. It's not just somebody might do something, but even what I'm interested in doing. It's hard to predict exactly which of those ideas that I'm interested in are going to land. And referring to that previous kind of wandering through the desert thing. The ones that you've listed have some very nice properties for other purposes. The ones that I'm specifically interested in exploring, I'm working on support for tessellation and displacement mapping on top of Nanite. I'm working on that now. I think displacement mapping is a very core tool for artists to be able to get that sort of geometry quickly and do so in a procedural way that's not really possible with Nanite right now. If they wanted to create, say, a wall with brick where the bricks are kind of, popping out of the wall, they can make a model of that wall with those bricks in that form right now, and then maybe tile that wall section as just, make tiling the mesh itself. But if they wanted to then make that brick and a sort of cylindrical tower and have that curve, they would need to make another mesh that's now that curved section. Where if it's a displacement map, you can have that same displacement map be on the flat wall, and then you throw it on a curved wall, and you can throw it on anything. And that same piece of data that sits on disk, the same amount of work from the artist can be applied to a bunch of different things very easily. And you can do so in ways that are kind of procedural, in the same way that people do procedural texturing. The same sort of shader logic applies here too. I think that's a really useful thing. I'm also really interested in exploring, going back to that voxel experiments that at the time I considered to be failures. There's some of those. This is kind of what I was alluding to, not just that it's necessary to explore ideas that fail, like failure is an important component to research and invention. But that's sort of like planting those seeds where you don't know what something's going to be useful always when you go into it, but you kind of rely on your experience and your intuition that comes from experience. Like, I've been doing this for a long time. It's really hard to quantify. Why am I interested in that thing? Sometimes it's very easy to argue like, oh, well, it's because of this, because I need it for this. But in other cases, it's just curiosity. There's a thing there that seems like it could have value, although I'm not exactly sure with what yet. Or I might have an idea of what I think it would be useful for at that time, but it turns out it's useful for something else. But there was something there that attracted my attention. And that's where that sort of hard to quantify intuition comes from. So I was exploring it then for one reason, and now I've got some other uses that voxels might be useful for in the future.
There's a lot of appetite and a lot of usage of subdivision surfaces. So how could you combine the benefits of the two workflows, Nanite and Subdiv? Did you think about that?
I'm hoping that an extension of the tessellation work that I'm working on now to try to support displacement maps can end up being extended to provide tessellation for subdivision surfaces or just higher order smooth surfaces, of whether they're subdivision based or something else. But in particular, subdivision is difficult. It is difficult to parallelize on the GPU. There are schemes to make that work, but at its heart, it's like a recursive operation. I mean, that's kind of by definition, it's a surface that is formed through recursive subdivision.
So, Brian, I wanted to ask you about scaling up to even bigger worlds, right? So, just my interest in graphics and the work we're doing at Cesium. We do like full globes. You can zoom in, you can see the terrain for the US. You zoom into Philadelphia, you see the buildings. You go inside the building, you can see a box on a table. It's all based on hierarchical level of detail that enables, view custom calling and inclusion calling, as you mentioned earlier. We do a lot of mesh decimation to pre-compute those things and have geometric error to kind of drive the LOD selection. And it seems like there's just so much synergy and maybe opportunity for Nanite to scale to that, and maybe even using some of the spatial data structures that we've worked on. Have you thought about this, and like how would you approach it?
It hasn't, that scale of things hasn't been the goal overall, but yeah, it should in theory be able to scale, though there would have to be some tweaks for sure, just to ramp up to the amount of precision needed at those bigger rates. Like we have a fixed bit precision for positions and stuff that it's just based on the bounds of the mesh from the starting point. So we'd need to add in some changes to support that sort of thing. But another kind of like key area that doesn't fit with for our current direction is that Nanite is built around the workflow of instancing right now, because that's just how our artists work in building out video game worlds. They'll take that one mesh and instance it all over the place and do a lot of kit bashing. So we'll have supporting very high instance counts into the millions is a thing that we can do that's pretty unique in the game world. But that doesn't scale up. Like there's a point where, I mean, even in some of the things that we have done and shipped already, like the Matrix demo that we did, the amount of total instances in that whole city environment was at least like 8 million, if not more than that. I don't remember exactly what the numbers were in the final form, but 7 to 8 million I think we had. But like scaling up to that extent is kind of past where Nanite is at least currently good to scale to. So we've got a feature in Unreal that predates Nanite, that was trying to deal with that problem before the counts were even anywhere near the millions. The one they were in the tens of thousands, it was trying to deal with them. That is, funny enough, called HLOD in the engine, which stands for hierarchical level of detail, which is really just a super generic name for lots of algorithms that end up working like this. But it's at least a bit more traditional scheme down that route, which is that the key difference there is that it is aggregating many objects together to form a mesh that is a unique mesh of some chunk of the world that replaces the many instances that came before it. Like it'll take all the instances, mash them all together, and try to make a single mesh out of them. But doing so with materials and shaders and such needs to have an aggregation of that stuff too. So it has it does a process of baking down those textures and that shaders and all of that stuff into a unique texturing over that unique bit of geometry. And then once you get to that point, and that's when you can start scaling up to the bigger things. Treating it as a bunch of individual objects just doesn't scale that far. The sort of example that I've given to try to demonstrate that of like, well, clearly there needs to be some point where this process happens, where like if you're flying in a plane over New York City and then you're looking down into some skyscraper, we're not going to want to draw the like coffee cup sitting on someone's desk that happens to be in some skyscraper in a city that's got tens of thousands of buildings. Just the amount of actual object count that you get at that point is billions, trillions of things. It's just not going to scale. But if you can aggregate them, then you can get down to the memory, the data scaling in a similar way to how I was explaining, where you want it to scale with your pixel count. And that's something that's actually practical to do when they're not separate instances. They're just one big chunk of data like Google Earth does, where you can fly around and see stuff chunked up, or Cesium has a similar concept. So switching over to that mode is something that Nanite could do. We could make a mesh in that sort of aggregated way, and we do that with the HLOD feature when we ship the matrix demo. For example, the meshes that it created, those unique meshes with its baked textures, those were Nanite meshes as well, and we could make all of it just one big Nanite mesh, and that whole hierarchy could be managed just by Nanite itself. It's not currently. Each one of those chunks of the city, it creates a Nanite mesh of, but there's not one Nanite mesh of all of them merged together just because it wasn't important. There's not enough of them that merging them together, having that hierarchy go all within Nanite was useful. But if we scaled up to that sort of scale, it would be necessary. We are looking into scaling up Nanite for other use cases from a modeling perspective, from an art creation perspective. That's interesting. We're looking at would it make sense for to have terrain geometry be like Nanite meshes and actually author them as meshes. So we'll see where that stuff goes, but that would be very large scale. It wouldn't be planet scale necessarily.
So one of the topics that Patrick and I, think a lot about and care a lot about is standardization. And so I have a few questions about, exploring the potential relationship of Nanite with standards. So, but first of all, have you come across other groups or individuals proposing alternative solutions for virtualized geometry? Are there any other implementations?
I mean, there's work done into standardizing model interchange formats, but those aren't virtualized. I think the only one that has happened that I'm aware of recently is NVIDIA's micromesh work. It's not standardized yet. In fact, the spec of it isn't even released, but
can you see similarities in the approach? Are we starting to see convergence of some ideas that seems to be good solutions?
Definitely not. Convergence, definitely not. So the micromesh approach from NVIDIA is more of a displacement sort of approach. It's not irregular meshes. That's kind of the fundamental structure of Nanite. So no, definitely not convergence there. I expected that there was going to be more competitors or copycats, I guess. Just like people following, because I've done presentations now on how Nanite works, as well as it's just been out, so people can look at it and try to dissect it and reverse engineer it, and that sort of thing for a few years now. So I expected that there was going to be more people trying to replicate what it does and how it does it, especially because the info of how it works has now been done SIGGRAPH presentations and stuff on how it works. So I expected there was going to be more people replicating the work, but I've yet to really see that in practice. We'll see. Maybe they're incoming any day now, but they haven't, or I'm not aware of any that have shipped yet, and any sort of like video game product or major engine.
And so, but those super high quality assets, as you mentioned, every artist wants them. Even Patrick for GIS workflows. I mean, So is there a path to see something like Nanite incorporated in standards like a GLTF, 3D tiles, or USD? What would be your recommendation there?
The source geometry for Nanite to build things off of, those can very well be standardized in the same form, GLTF for USD or whatever sort of interchange formats for the source geometry. All of that's fine. But trying to standardize what the like compressed representation, for lack of a better word, it's kind of would be the difference between standardizing Targa file or something like that versus standardizing JPEG, which obviously is a standard. The tricky bit for Nanite is there's a lot of different a lot of different aspects of it that makes it more difficult. For one, it's in rapid development, so there's things that are still changing about Nanite pretty regularly, such that we bump the version number on Nanite probably almost monthly this phase, and certainly every Unreal Engine release at this point, I'm sure has had a version bump in it, but we bump it even more often than that internally because we've made some sort of format change. Now, some of those changes don't need to be actually binary format breaking. They're instead just changes for how we build the data, because we've if you could think about it, there is the encoding of JPEG, and then there is a better way to generate that same encoding that looks higher quality, but would be compliant in any JPEG viewer. It wouldn't result in the same binary data, obviously, or otherwise you wouldn't have changed anything. But as comes out with a different JPEG file that looks better, but is still viewable by the same viewer. So there are changes that we make to that we bump the version number for, just for reasons I won't go into. So there's some of those that we don't need to bump, but there are still ones that are actually compatibility breaking changes that are good changes for us to make. They result in things either compressing better, being smaller data, or faster to render, supporting the addition of new features, or new features being added that can be performant that otherwise wouldn't if they didn't come with those changes. So some of that would be problematic if we kind of locked down a particular format that it's at. But a next step there that would seem like it would be, the solution is, now you have a version 1 and you've got a version 2 and you've got a version 3, and each one of those could be standardized. And in some file formats, that's fine, that you could have this sort of versioning and backwards compatibility and all that. That's much harder, if not impossible, in the current form of Nanite, because of how GPUs work and the particular way that the compute shader rendering works with Nanite. We have a single shader that runs in this, it gets very nerdy here, but it runs in this persistent threads single dispatch mode to be efficient. and that processes it does the level of detail and occlusion culling of all of the clusters that Nanite will draw of the entire scene. Breaking that up into multiple different shaders and different compute dispatches would be far less efficient, and trying to get the logic from many different versions and decodings of the geometry all into some of these single shaders would make that shader far less efficient. So it would be possible, but it would also be kind of like damaging to Nanite's performance and in some cases functionality to try to get many meshes with different versions in the same scene at the same time. So if all of it could be one version or all of it could be another, it'd be fine. But if you want to mix and match, the performance drops. So those are all considerations in what it is right now. As it gets more and more stable over time, as the development slows, which inevitably will happen. It's not happening right now, but inevitably the pace of these changes will slow down. Then it could start becoming more realistic. I think there is a possible thing that could happen here that could make it happen in a somewhat shorter time frame. And that would be if there was a reason to implement what Nanite is doing in hardware. Whether for a variety of reasons why that might be a thing to do, one of which would just be, well, we're going to make, fixed function hardware ASICs or thing to make exactly what Nanite is doing way faster than what we'd run in software shaders. But it's still rasterizing and doing the same thing that it's currently doing. I think what would be more likely of a future for this to happen, if it would happen, would be to implement Nanite's data structure in a way that is fast to ray trace, which is not currently the case. If that happened, say NVIDIA, AMD, whoever, Intel wants to make fixed function hardware for this like encoded triangle cluster sort of format, with the ability to change which clusters are picked due to some level of detail properties. Being very hand wavy right now because it's hard to say exactly like how this would go down. But if something like that happened, where the specific format was done not exactly our encoded format, but an encoded format that would get at the goals that Nanite is trying to do, but one that would be very fast to ray trace against, we would be very compelled to support specifically that format with Nanite, because it would mean for our ray tracing data to ray trace against it, we can ray trace against the same data. And it would be probably silly for us to have the ray tracing version and our current encoding that are just slightly different from one another without like a big benefit. Even if that other form is slightly bigger from a compression point of view than what we currently have, just the fact that we'd only have one of them instead of two parallel data types would be compelling enough for us to support specifically that standardized that hardware version, and then for that to really be something that would have a big impact across the industry. Everybody, all parties involved would have good reason to try to standardize what that format was. Otherwise, it probably wouldn't be used if it was only on a single vendor's hardware, unless it was a console. But if in the PC space, there's different GPUs out there, and standardization through DirectX or Vulkan or whatever is important to get the rollout of features like that. So I could see that feature possibly accelerating standardization of a Nanite-like data format, but it's hard to say.
Brian, it's been a ton of fun chatting with you. I love these deep technical episodes. So thank you so much. We love to wrap up. If you want to give a shout out to an individual or organization.
I guess I just say shout out to Epic Games. Thanks for enabling me to do this work. And I call out in particular the rest of my team, Grant Wyadol and Rune Stoop, and Jamie Hayes, who are working with me on on Nanite stuff. Also, Andrew and Ola that are working on the shadow side of Nanite.
So, Brian Karis, you are a geek, you are a nerd, you're a mathematician, you're probably an elite programmer, but I want to conclude the podcast with a quote of you, which I think is very interesting and very telling and very unique. When you said in a presentation recently that, and I'm going to read you, in my opinion, there is no bigger problem in my field than making 3D content cheaper to create, than making the art of creating it more accessible to more creators, and knocking down every last impediment left to artists manifesting their vision. I think I want to congratulate you and thank you for that, because that focus on artists is, you also said about computer graphics is all about helping artists or something like that. I think it's a very unique and very interesting point of view, and thank you on behalf of everybody. Thank you very much for your contribution, and thank you very much for being with us today.
Well, thank you for having me.
Patrick, thank you too. We'll see you in the next episode of Building the Open Metaverse.
Looking forward to it. Thanks, everybody.